Hello everyone! Have you ever wondered how we can find the volume of objects with curved and irregular shapes, like a vase, a bottle, or even parts of machines? These shapes don't follow simple formulas like length times width times height. So the question is, how do we measure their volume accurately? This is where calculus becomes useful. Instead of finding the volume all at once, we break the shape into very thin slices. By understanding each slice and adding them together, we can determine the total volume. When a flat region is rotated around an axis, it forms a three-dimensional solid, and depending on how we slice that region, we get different shapes that help us compute the volume. To better visualize this process, let's look at how slicing and rotation work together. Let's start with the disk method. In this illustration, notice that the region is being rotated around an axis and it completely touches that axis. Because of that, there is no gap inside the solid. If we slice the solid perpendicular to the axis of rotation, each slice forms a solid circular disk. That's why we use the disk formula, where the volume is built from the area of these circular slices. The key idea here is simple. No hole, just solid disks stuck together. Now, let's look at the washer method. In this case, the region being rotated does not touch the axis. As a result, when the solid is formed, there is a hollow space in the middle. If we slice this solid, each cross-section looks like a washer, a circle with a hole. So instead of just one radius, we now have two, the outer radius and the inner radius. We subtract the inner area from the outer area to get the volume of each slice. Finally, we have the cylindrical shell method. Here, instead of slicing across, we slice parallel to the axis of rotation. When the region rotates, each slice forms a thin cylindrical shell like a hollow tube. These shells wrap around the axis, and their volume depends on the radius, height, and thickness. So instead of stacking flat disks, we are stacking thin cylindrical layers. This method is especially useful when slicing the other way would be more complicated. So depending on how the region is sliced and its position relative to the axis, we get different shapes, like the discs, the washers, or cylindrical shells. These methods allow us to compute the volume of complex solids with accuracy. They are widely used in real-life applications such as engineering design, manufacturing, and even in modeling objects in science and medicine. Now that we understand the concepts behind each method, let's see how they are applied in solving problems. Let's find the volume of a solid generated by revolving the region bounded by y equals 1 over x, y equals 0, x equals 1, and x equals 4 about the x-axis. But before we set up the integral, we first need to visualize the region. By plotting the function y equals 1 over x in the boundaries, we can clearly see the area that will be revolved. We start by selecting values of x between 1 and 4 and calculate the corresponding values of y equals 1 over x. These points will help us plot the curve accurately. Next, we plot these points on the coordinate planes and connect them smoothly. This gives us the curve of y equals 1 over x. We also draw the lines y is equal to 0, x equals 1, and x equals 4 to define the boundaries of the region. We then shade the region enclosed by the curve and the boundary lines. This shaded area is the portion that will be revolved around the x-axis to form the solid. Now that we have visualized the region, we can now solve for the volume. Since the axis of rotation is the x-axis and the region touches the axis, we use the disk formula. The volume formula is volume is equal to pi times the integral from a to b of the square of f of x with respect to x, where f of x is the distance
from the x-axis to the curve, or the radius. Next, we determine the interval and function. The curve y equals 1 over x is a radius at each point along the x-axis. The bounds of integration are x equals 1 to x equals 4 as given by the vertical lines. Then we set up the integral. Substituting the function into the formula, we set up the integral as volume equals pi times the integral from 1 to 4 of the square of 1 over x with respect to x. Then we simplify the integrand, in which we have 1 over x. We made it as x to the power of negative 2 to make it easier to integrate. Next, we integrate. Integrating x to the power of negative 2 gives negative 1 over x. So the volume integral becomes volume is equal to pi times negative 1 over x evaluated from 1 to 4. Now we evaluate. At x equals to 4, we substitute this value to negative 1 over x. Now we have negative 1/4. And then at x equals 1, we substitute it to negative 1 over x. Now we have negative 1 over 1. Simplifying it, we have pi times negative 1/4 plus 1. Negative 1/4 plus 1 is equal to 3/4 times pi. Now we have 3 pi over 4 cubic units. Therefore, the volume of the solid formed is 3 pi over 4 cubic units. Now we are going to find the volume of a solid generated when the region bounded by y is equal sine x and y equals cosine x over the integral, where x lies between 0 and pi over 4, is revolved around the horizontal line y is equal to negative 1. But again, before we set up the integral, we first need to visualize the region clearly. By plotting the graphs of these two functions, we can see which curve is on top, which is on the bottom, and the area that will be revolved. Now let's start by constructing a table of values for y equals sine x. We select several values of x within the interval and calculate the corresponding values of sine x. These ordered pairs will help us plot the sine curve accurately. The same thing that we did when we construct a table for y is equal to cosine x, using the same x values. This allows us to compare the two functions and identify the region enclosed between them. To make the graph easier to read, we use different colors or markers for each function. Each point is paired with its coordinate value, so we can clearly see which points belong to sine x and which belongs to cosine x. We begin by plotting the points for y is equal to sine x on the coordinate plane, and after placing the points, we connect them smoothly to form the sine curve. As you can see, the curve gradually increases over the interval. Next, we plot the points for y is equal to cosine x on the same graph. Connecting these points forms the cosine curve, which decreases over the interval, contrasting with the sine curve. With both graphs drawn, we can see the relationship. Over the interval, y equals cosine x is above y equals sine x, and the curves intersect at x equals pi over 4. The region between these curves is what we will revolve around y is equal to negative 1, as you can see in the graph on the left. Then we shade the region between the curves. The shaded area represents the exact portion that will be revolved. Clearly identifying this region is important because it defines the outer and inner boundaries of the solid. Now that we have visualized the region, we can now solve for the volume. First thing first, we identify the method. Since the axis of rotation is horizontal and below the region, we will use the washer method. The formula for the volume is equal to pi times the integral from a to b of the difference of the square of f of x, which is the outer radius, and the square of g of x, which is the inner radius, with respect to x. The next thing we will do is we determine the interval. Looking at the graph, the top curve is y is equal to cosine x and the bottom curve is y is equal to sine x. The axis of rotation is y is to -1, which is below the region. This tells us that the distance from the axis to the top curve is the outer radius and the distance from the axis to the bottom curve is the inner radius. Now we identify the radii, in which our outer radius would be cosine x plus 1 and our inner radius will be sine x plus 1. Next, we set up the integral. Substituting the outer and inner radii in our formula, we get volume is equal to pi times the integral from 0 to pi over 4 of the difference of cosine x plus 1 squared minus sine x plus 1 squared with respect to x. Next, we expand both squares. So cosine x plus 1 squared becomes cosine squared x plus 2 cosine x plus 1. And sine x plus 1 squared becomes sine squared, or sine x plus 1 squared becomes sine squared x plus 2 sine x plus 1. We simplify them, canceling all ones. We get cosine squared x minus sine squared x plus 2 cosine x minus 2 sine x. Then we use the identity cosine squared x minus sine squared x equals cosine 2x. This becomes cosine 2x plus 2 cosine x minus 2 sine x dx. Now we integrate them term by term to find the antiderivative. The integral of cosine 2x dx is equal to 1/2 sine 2x. The integral of 2 cosine dx is equal to 2 sine x. And the integral of -2 sine x dx is equal to 2 cosine x. Now we evaluate them at x is equal to pi over 4. Substituting it to the equation, we have 1/2 plus 2 times the square root of 2. And in substituting 0, we have 2. Now, subtracting them, we have 2 times square root of 2 minus 3/2. Now, we multiply pi to that. We have pi times 2 times square root of 2 minus 3/2 cubic units. Therefore, the volume of the solid generated when the region bounded by y is equal to sine x, y is equal to cosine x, and when x lies between 0 and pi over 4 is revolved about the line y is equal to -1 is pi times 2 times the square root of 2 minus 3/2, or approximately 4.1734 cubic units. For the third example, let us find the volume of the solid obtained by rotating the region bounded by x equals 1 plus the square of y minus 2 and x equals 2 about the y-axis. But before setting up the solution, we first need to visualize the region by constructing its graph. To begin graphing, we construct a table of values for the function x equals 1 plus the square of y minus 2. We now select values of y from 1 to 3 and compute the corresponding values of x. These points will guide us in accurate what? Okay. Now for the third example, let us find the volume of a solid generated by revolving a region about the y-axis. The region is bounded by the equations x equals 1 plus the square of y minus 2 and x equals 2. But before setting up the solution, we first need to visualize the region by constructing its graph. To begin graphing, I constructed a table of values for the function x equals 1 plus y minus 2 squared. We select values of y from 1 to 3 and compute the corresponding values of x. These points will guide us in accurately plotting the curve. Next, we plot these points from the table on the coordinate plane and connect them smoothly. This forms a parabola that opens to the right, with its vertex at point 1, 2. We also graph the vertical line x equals 2, which serves as the right boundary of the region. After plotting the curves, we shade the region enclosed between the parabola x equals 1 plus the square of y minus 2 and the line x equals 2. This shaded region represents the area that will be revolved about the y-axis to form a three-dimensional solid. Now that we have visualized the region, we can now start solving for the volume of the solid. First, we determine the limits of integration. And to find it, we must find where the two curves intersect. So we set 1 plus the square of y minus 2 equals 2. Solving this, we get the square of y minus 2 equals 1. Square both sides is equal to 1 minus 2 equals the positive and negative 1. And so y is equal to 1 and y is equal to 3. Therefore, the limits of integration are from y is equal to 1 to y is equal to 3. Now that we have established the limits, we can identify the appropriate method to use. Since the region is revolved about the y-axis and the functions are expressed in terms of y, we use the cylindrical shell method, where volume is equal to 2 pi times the integral from a to b of radius times height with respect to y. In the cylindrical shell method, we identify two important components, the radius and the height. The radius is the distance from the y-axis to the shell, which is x is equal to 2. And the height is the difference between the right and left boundaries. For the right boundary, we have x equals to 2 and left boundary is equal to x equals 1 plus y minus 2 squared. So the height becomes 2 minus 1 plus the square of y minus 2. Simplifying it, it will become 1 minus the square of y minus 2. Now we set up the integral. We substitute everything into the cylindrical shell formula, which gives us 2 pi times the integral from 1 to 3 of 2 times 1 minus y minus 2 squared with respect to y. And simplifying it becomes 4 pi times the integral from 1 to 3 of 1 minus the square of y minus 2 with respect to y. To simplify the integral, we use u substitution. So we let u be equal to y minus 2. So du becomes dy. When y is equal to 1, u becomes negative 1. And when y becomes negative is equal to 3, u becomes 1. The integral becomes now volume is equal to 4 pi times the integral from negative 1 to 1 of 1 minus u squared du. Now we integrate. The integral of 1 minus u squared is u minus u cubed over 3. Evaluating from negative 1 to 1, we get 1 minus 1/3 minus negative 1 plus 1/3. This simplifies to 2/3 minus negative 2/3, which is equal to 4/3. Finally, multiplying by 4 pi, we obtain the volume, which is equal to 4 pi times 4/3 equals to 16 pi over 3. Therefore, the volume of the solid form is 16 pi over 3 cubic units.
To summarize, finding the volume of solids of revolution is all about understanding how a shape is formed when a region rotates. We use the disk method for solid shapes, the washer method for hollow shapes, and the cylindrical shell method when working with vertical or horizontal slices that form shells. The key step in every problem is identifying the correct method and expressing the radius and height properly. Once that's done, the rest becomes a matter of setting up and solving an integral. With practice, you'll be able to visualize these solids more easily and choose the right method with confidence. Thank you for watching.